This device here is called a ballistic pendulum, and it's a model of an old-time way where people used to measure the velocity of a bullet coming out of a gun by measuring how high it made a pendulum rise once the bullet hit it. So this is a classroom model, and that brass ball on there is going to get fired into this pendulum, and then we're going to see how high it rises. Based on the height, we'll be able to calculate the original velocity of the ball. So I'm going to stop the pendulum. We'll fire the gun. And now we can zoom in on here, and we can basically figure how high above the base of the device that this went. In the next few problems, we're going to look at how we can use this to figure out how fast the ball left the gun. It's important to recognize that this is not a simple problem, that there's actually several distinct snapshots in time that we have to look at. The first snapshot in time is when the ball is leaving the gun. The second is when the ball is just hitting the target and a collision is just happening. And the third is when it's all moved to its maximum height. In order to accomplish the problem, we're going to have to relate these snapshots to each other using separate problems. So I've got these three snapshots on the board. This is a complicated problem, and to move between the first time when the bullet is not in the block yet, but is about to hit, to the second time where it's embedded in the block but hasn't started to rise, to the third time where it started to rise, we have to use different strategies. And I want to focus on the time between these two snapshots as one problem, and the time between these two as another one. Let's go through all the strategies we know for solving problems right now and try to come up with the right one. So between snapshot 1 and snapshot 2, what's happening? The bullet is embedded in the block. So we know this is not a motion problem using the kinematic equations, the three simple ones, because we have a variable force. As the ball goes in, the force is going to be complicated. It's going to have some pattern. Who knows what it is? It sure isn't constant acceleration. So we can throw those out. We can also throw out conservation of energy, because we know work is being done by a non-conservative force of friction. And that energy is being lost as heat, which we're not catching. We're not finding some way to measure that. So conservation of energy is out because we just have no idea how much work is being done. But we have a collision going on, and we know that momentum is usually a good strategy. There's quite a bit of friction as the ball goes into the pendulum. So in these collisions where there are non-conservative forces, momentum is often a really good choice. And momentum is appropriate because although the ball puts a force on the pendulum also puts a force on the ball. So there's no external forces. So conservation of momentum is a really good strategy for this section. Between snapshots 2 and 3. Well, in this case, conservation of momentum is a bad choice because we do have an external force acting. We have the force of gravity. That's not a force between the bullet and the block in this case, and it clearly is affecting our momentum. Gravity is going to be slowing down as we rise up. So momentum is a bad choice here. Kinematics equations are not a great choice either. We have a centripetal acceleration. The tension force is changing its direction as we swing up. Gravity's not. So that's resulting in an acceleration that's changing as we go through the path because those two forces are changing their directions. So forces are not a good choice. But since we're moving up in a gravity field, conservation of energy is a great choice. Here we have a lot of kinetic energy. Depending on what we call our zero height, we may have potential. It usually makes sense to call the lowest point the block's at zero height. We're rising, so at the end, we have potential energy. So conservation of energy is great for relating these two times. Remember, the overall goal of the problem is to relate how high the block goes to the original speed of the bullet. So what we'll do, we'll figure out from how high it rose, we'll figure out how fast this block was going once the bullet was in it. Once we know that, we'll use conservation of momentum to figure out how fast the bullet was going before it hit the block.
So the data we have here is from this YouTube video, which is awesome. Somebody shoots a .22 caliber rifle into a wooden block hanging on a string. It's one that we watch in class, and it's a good introduction to solving these problems. We're ultimately trying to get the speed of the bullet, like we said before. So we're going to work backwards. We're going to start with how high the block rises. On this YouTube video, they shot it in front of a wall with stripes on it, and they gave us the width of the stripes so we could count how many stripes up we got and figure out how high it had gone. So that's what this calculation is over here. The height ended up being 0.48 meters. So the first step was to go between snapshot 3 and snapshot 2. So we said that that's a conservation of energy problem. It has kinetic at the beginning, potential at the end. We plug in our equations, and that tells us that the velocity of the combination of bullet and block after the bullet hit is 0.307. H is pretty easy to get. There's not much mass on the string, so we just go from the middle of the block on down. We'll have to look at that assumption later for other ballistic pendulums. To go between snapshot 1 and snapshot 2, we said that would be conservation of momentum. And we had 2 objects before and 1 after. So there's their momentum equation. So that gives us an original velocity of the bullet of 331.32 meters per second. We're going to look in a second video at some experimental considerations when doing this in class. There's 2 classroom models that are commonly used, and I think both teach some interesting physics, and I want to talk about how to use both of them.